Okay, good afternoon, everybody. My name is Marina Gemma. I am a planetary scientist, and I am going to be telling you guys all about meteorites. And I'll first start with the difference between a meteor and a meteorite, because terminology is a bit of a sticking point in this field. Um, so there we go. So a meteorite is defined as a solid body of extraterrestrial material that makes its way to Earth's surface. Um, but a meteor, which we hear, I think, probably more commonly in like pop culture and whatnot, is also called a shooting star. That's what you call that same material when it's in the atmosphere. But this material starts on an asteroid in outer space. And let's say a chunk gets broken off an asteroid, then you call it a meteoroid, then a meteor when it's in the atmosphere, and a meteorite when it's on the ground. So it's all the same material, it's just different terms for the same thing, but it can get a bit confusing. So I'll kind of go through my Meteorites 101 spiel, both the science and the more practical side of things, to kind of give you guys a background on what I do and what might be interesting in regards to the hackathon challenge. So I like to start with where they found. I told you they come from asteroids, but once they land on the surface, where do we find them? It would be really nice if all meteorites left craters like this. They'd be very easy to find. This is Meteor Crater in Arizona, which is kind of a misnomer. It should be called Meteorite Crater, right? Because it hit the ground. So there's tons of confusing terms here. But this is about 4,000 feet in diameter, the crater itself. And this was caused by a meteor that we estimate to be about 150 feet in diameter. There's a large difference between the size of the actual impactor and the crater that it made. And for scale here, you can kind of see there's a semi truck and some school buses in the parking lot here. So that gives you a sense of scale for this crater. And this is actually one of the best or the best preserved crater in all of Earth's surface is in Arizona. So that's pretty cool. Uh, but most meteorites that we have in collections are actually much smaller. They're about the size of your hand. And these are just some of the examples that we have up at the American Museum of Natural History where I work. A lot of them have this kind of dark outer rind that we call a fusion crust. That's what happens when these rocks come through the atmosphere. The outside of them completely melts because of the friction with the air in the atmosphere. And that's one of the first things you look for if someone were to bring you a rock and be like, is this a meteorite? You ask, does it have a fusion crust? If it doesn't, probably not a meteorite. So these are actually mostly found in deserts, Antarctica predominantly, and the Sahara Desert. And that's just because they're easier to find in these places. You can imagine coming across, a shiny dark rock in the middle of the Sahara or in the middle of an ice field in Antarctica is a lot more convenient than trying to find one rock in an entire forest. Um, but it's not because more of them fall there. So meteorites fall, there's hundreds that are falling to Earth every day. This is a map of what we call bolide events. So that's just basically a airburst larger than, I forget the exact definition, but basically a meteor that's detectable by radar. So this is a map of those events between 1994 and 2013. And you can see that there's really no preference for a certain region of Earth where these things are falling. They're falling all over. Most of them, right, are going into the ocean. That's over 70% of the surface. Those we never see again. But the ones that do fall in the deserts, they're just easier to recover. And NASA sends teams to Antarctica every year to kind of comb the ice fields and pick up those meteorites for further study. So how did they form? This is getting more into the science of things. We have to go all the way back to the early solar system. So after the sun formed, there was this leftover disk of gas and dust surrounding it. And this we call the protoplanetary disk, so before planets existed. And as this disk started to cool, you started to get minerals solidifying. So just teeny little kind of pebbles, you can think of them as. And over time, these minerals started to accrete or stick together to form what we call undifferentiated planetesimals. These are really what asteroids are. So they're just lumps of smaller things. But over time, if you kept accreting, you could eventually turn into a differentiated body or a planet. Basically, you just have to pass a certain mass. You have to have enough gravity for a planetesimal to separate into layers. So a core, a mantle, and a crust, like Earth has, and like we think the rest of the terrestrial planets in our solar system have. And the reason that we kind of know these things is because meteorites can sample these different layers. So collisions in the early solar system fragmented these kind of baby planets. And these pieces hung out in the solar system, mostly in the asteroid belt, and some of them eventually fall to Earth as meteorites. So what do these things tell us? Once we have samples on the ground, we can study them in the lab, what kind of information are we getting? So I kind of alluded to this, meteorites can tell us about planetary structure, right? These baby planetesimals that were broken up into bits. There's parts that sample the core, the mantle, and the crust of these objects. And since we're never going to be able to drill all the way down through the layers of the Earth, this is one of the only ways we know what planetary interiors really look like. So iron meteorites tell us about what the cores are made of, right? Iron meteorites, mostly iron, some nickel, other metals, heavy metals that sink to the center. We have meteorites that we think are from the mantle of these objects. They're really rich in this mineral olivine, which is mostly what Earth's mantle is made of. And we also have meteorites from the crust. And these are actually the meteorites that are most similar to rocks on Earth because we really can only sample surface rocks on Earth, and meteorites from the crust of other planets actually look a lot like Earth rocks, which is pretty cool. And of course, we also have meteorites from the moon and Mars. These are called achondrites. That just means they're from differentiated bodies. And that tells us obviously a lot about what those objects are made of without ever having to go there. So meteorites are really cool. It's like free delivery of samples in the solar system. So I am very interested in the early solar system and what was going on during that time, right around the time of planet formation. And so I study those undifferentiated meteorites, so those just globs of the early condensed material that stick together. And so we can look at those and learn more about the age of the solar system. So one of the particular objects that scientists have looked at are called calcium and aluminum inclusions, and they've isotopically dated those to get an age of the solar system. And this is really easy to remember. It's 4.567 billion years old. And so that's the oldest solid object we have in our solar system after the sun formed. So meteorites can also tell us about asteroids. Now I'm getting more into maybe the challenge relevant kind of side of the science, right? What are asteroids made of? What is their structure? What is their history? And one of the ways we do this is we use computed tomography to look at the three-dimensional structure of meteorites. So this sample I'm showing you is about the size of like maybe the top of your pinky finger. It's pretty small. But we can map it in extremely high resolution using the same kind of technology that you would use if you were to get like a medical CAT scan. And this maps, CT essentially maps densities. So the really kind of bright regions that you're seeing are the metal in these undifferentiated meteorites. And as the material gets darker, that means it's less dense. And so effectively has less metal, less of those heavy elements. And this is really interesting because we can start to learn about what kinds of processes existed or happen on asteroid parent bodies. So, was there any kind of collisions happening? Was there deformation happening? Was there compaction? Was what kind of, thermal metamorphism was occurring on these asteroids? This is kind of how we can get at that question and what I'm showing you here is the same meteorite data from the last slide, but we've just generated a 3D model of it, and that allows us to segment out different components based on their density. So when it reduces just to that orange material, that's the metal. We can quantify how much metal there is and do this for all the rest of the minerals in the meteorite as well. So we're getting, statistical information out of this as well, not just looking at the morphology of this kind of material. So why are they important? I think this more directly relates to the challenge, right? What we learn in elementary school is most asteroids are in the asteroid belt. They hang out between Mars and Jupiter. But the reality is there's a lot of asteroids and they can be hazardous. And the more we look, the more we find. And it's true that most of the asteroids hang out in the asteroid belt. So that's what you're seeing here in yellow is the main belt asteroids in between Mars and Jupiter. But there's a lot of different asteroid groups that exist outside of the main belt. Some are located around Jupiter. Those are called Trojan asteroids, which I think are about to turn on in this video. Maybe my timing might be off. There they are. The Trojan asteroids, they orbit in Jupiter's orbit. And there's also a probably more relevant class of asteroids that are found closer to Earth. These are the near-Earth asteroids. And there's a subset of those called the potentially hazardous asteroids. So the ones in orange are near-Earths, and the one in red, I don't know how well the colors are coming across, are the potentially hazardous asteroids. And we can track their movement. And if you do, you see that there's millions and millions of objects whizzing by Earth all the time. So this is sped up, obviously. Earth is spinning really fast, but this is looking at the dynamical movements of these objects. And we can track those through time. But one of the limitations is that we can't detect small asteroids. And small asteroids is like maybe 100 meters or below. So there's still, that's a couple hundred feet, right? Like they could still do a bit of damage, but we are kind of up against some technological limitations there. But the good thing is that NASA has dedicated a telescopic survey to finding these. It's called NEOWISE. And these telescopes just stare at the sky and are waiting for objects to move across them. And the more they look, the more that they see. I think this is maybe this animation is over 10 years, I want to say. It starts in 2014. Yeah, maybe to like 2024. So the near-Earth asteroids are in green, main belt asteroids are in gray, and comets, which I'm not really going to go into, are in yellow. They have a lot more eccentric orbits. But yeah, there are dedicated efforts to better understand these objects, which is good. And I feel like I probably don't really need to motivate this, but obviously these things can be hazardous. We see evidence of this throughout history. There's impact craters all over Earth. There's only a few impact craters that are over 100 kilometers, which includes the Chicxulub crater, which is what kind of spelled the beginning of the end for the dinosaurs. And so those are the ones, right, we're most concerned about from a practical point of view, from a planetary defense point of view. But the good thing is that they're pretty anomalous, and we think that the ones that are capable of making craters of that size are mostly trackable at this point. So the near-Earth asteroids, just to put some numbers on it, there's almost 40,000 known near-Earth asteroids. And I just checked this morning. There's actually one found yesterday is the most recent one discovered. So NASA updates this daily. And these are asteroids defined as approaching less than 1.3 astronomical units. from the sun. So Earth is at 1 astronomical unit. So basically asteroids that orbit within 1.3 astronomical units. And there's a subset of these, which I referred to before, called the potentially hazardous asteroids. And these have a stricter definition. This means that they come within basically 20 times the distance of the moon to Earth. So if you were to take the distance from the Earth to the moon, 20 times that, if an asteroid passes within that, it's potentially hazardous. Not It's just purely based on distance, not necessarily trajectory that it's going to hit Earth, just the fact that it moves that closely, because we can't predict its orbit that far out. So this is a little outdated. There's about 2,300 known as of November 2022, and only 153 are greater than a kilometer. So that's pretty good news. But one of the near-Earth asteroids that you might hear about in the news is called Apophis, and it's going to pass within 20,000 miles of Earth in 2029. And if you are really good with your satellites, you'll recognize that that means it's passing within geostationary orbit. So geostationary orbit satellites are, I think, like 22,000 miles. And this is going to pass within 20,000 miles. So it's pretty darn close. It's about 1,200 feet in diameter, but is not predicted to impact, just really whiz by very closely. So hopefully it stays that way. But Chelyabinsk is a meteor and meteorite that landed in Russia in 2013. And some of you might remember this. And it's a really good example of what a fairly small meteor and meteorite can do. Let's see, I don't know if this is going to play, but yeah, there's all of these like surveillance videos that capture the shockwave that happened from this meteor. And it didn't kill anybody, but I think thousands of people were injured just from like the glass that was blown out and things that hit them from the shockwave. And what was really shocking about this event is that we didn't know it was coming. So I think Chelyabinsk, off the top of my head, it was just like tens of feet in diameter. I don't think it was more than like 50 to 100 feet. But what really kind of saved the situation is that it came in at a very oblique angle in the atmosphere. So it experienced a lot more friction because it went through a lot more atmosphere than if it had just come in pretty perpendicular. So one of the things that made this one difficult is that our telescopes are limited to nighttime observations, right? They can only look in one direction. But Chelyabinsk was a meteor that came from the daytime side. And so there's no way, even now, that we could detect something like this. And so daytime meteors remain a ongoing kind of challenge for scientists. And it's, just comes down to more and more observations, not only from nighttime side, but from telescopes as well. The small objects remain difficult to detect with current technology. So anything less than, I think I said 100 meters. So Chelyabinsk was, again, I think around 50 feet, but up to a couple hundred feet, we still can't detect. So more data. This I like to just give as a fun example to show you the kind of data that astronomers are working with. So this is on the top, you have raw radar data of asteroid Cleopatra, which is a main belt asteroid, but it's 220 kilometers long. So this is massive. And this data across the top is what we get in our observation. And so you can then kind of play around with that data, simulate it, and form a shape model and get the estimated shape of Cleopatra. But this is a ginormous asteroid, and this is the best data we have. So it's worth, not to get on my soapbox, but this is I think, worthwhile investment of time and effort from NASA to better characterize these things and get more data as we move forward and our technology improves. There's also been a lot of missions to near-Earth asteroids in recent years. You might have heard of these. OSIRIS-REx was NASA's sample return mission. The Japanese space agency JAXA has also had two of its own sample return missions. And these are like the best thing in the world for scientists like me, right? It's, going to an asteroid, getting a sample, returning it, and we're able to study these things in the lab. And this allows us to improve our understanding of our remote observations, right? Because we can directly compare uh, observations we made on Earth of these asteroids and our predictions of their compositions and their structures to the samples that are returned. So this is really invaluable in bettering our understanding of these objects, is these sample return missions. And kind of on the planetary defense side of things, NASA had a mission called DART, the Double Asteroid Redirection Test. And this was essentially testing what would happen if we had to deflect a potentially hazardous asteroid from hitting Earth. So they chose a system that has no possible chance of ever being hazardous to Earth. And they sent a spacecraft and they impacted, it's a binary system, so it's an asteroid with its own moon called Dimorphos, and they sent the spacecraft directly into Dimorphos and just watched what happened. They wanted to see how much they could deflect its orbit through impact, right? Was it going to burst into 100 million pieces and just have a rubble pile of material still coming at us? Was it going to just absorb that impact and kind of slow down in its orbit, right? There's a ton of different scenarios that could have happened, and this had never been tested before. So this got, I don't know why, but I don't think it got a lot of like press coverage, which I found really interesting. I think it's one of the most interesting missions in the past couple decades that they've done. But by all accounts, it was a success. They got all the measurements they wanted to get. They were able to track the deflection in Dimorphos's orbit, and this really improved all of those kind of planetary defense planning scenarios that NASA had developed but never really obviously deployed. So I think, how much time do I have? I could end there, but I'll just go a couple more minutes. And I think something that people love talking about is asteroids as potential resources. So these are often thought of as potentially being raw materials for space exploration, right? They have water and usually in the form of ice. So that would be for not only human survival, but also rocket fuel. And people are also looking to maybe use this kind of material on Earth. So asteroids are dense in precious metals and rare earth elements, right? I talked about them as undifferentiated bodies. So this material is distributed throughout the asteroid rather than in differentiated bodies. Most of the heavy metals, right, the precious metals, have sunk down to Earth's core, and that's where they're sequestered. So we still have like a very small amount in our crust. That's what we mine. That's what we use for our electronics. But asteroids have these materials in relative kind of abundance. And this is just an example of one of the meteorites we have at AMNH on Agido. It's on display in the center of the room. It's a remnant of a planetesimal core. It's an iron meteorite. And if you want to actually look at the numbers, you can see that the density of, let's say, platinum in this meteorite is it's 3 times more dense in platinum than you would get from terrestrial ore. So again, this is one of the reasons people are interested in them, not necessarily from a scientific perspective, but more practical perspective. And these iron meteorites in particular are of interest. And NASA is actually sending a mission to an asteroid called Psyche. It has been valued at $10,000 quadrillion, which I think is just a fake number. And it's thought to be just a giant iron meteorite, so like Onagito, but way, 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 way bigger. It's 226 kilometers thereabouts in diameter. And compare this to Bennu, which was the target of NASA's OSIRIS-REx mission. This is just a paltry, $67 million. It's much smaller, obviously, but there's this question of, I want to know what asteroids are made of because I'm interested in the science that can tell me, but there's a whole contingent of people that are interested in these objects, right? Because they're interested in their economic value. And there's this website I found. I have no idea, again, where these numbers are coming from or if they're right, but basically you can plug in an asteroid and it will give you its purported value, if you want to look at that. But I think that's where I'll end. I don't know if there's a medium for taking questions, but I would be happy to do so if anybody has any. But yeah, thanks for letting me talk your ear off about space rocks. Yes, I will stop sharing there. Yeah.
Right. I can pin your video.
Thank you.
This is like some weird Jedi thing.
Yeah.
Because and then once you share your screen, it'll come up on here too. Just check my shirt.
You have those for our.
Share. A screen. Yeah, perfect. Okay, cool.
You ready to?
Thank you.
Oh, I will show you up.
Okay, hey folks. Thank you very much for thank you folks. I'm going to be chatting about some things you can do with Cloudflare. So we're sponsoring this event. Thank you for having us. We have a competition that we're running here for the local prize. There's the best use of Cloudflare developer platform. So there's a bunch of people wandering around who can help mentor. I'm also going to be judging that prize tomorrow. Winners will receive $5,000 of Cloudflare credits for a year, 3 enterprise domains for a year, and I think much more interestingly for all of you guys is skip the line for software engineering internships next year. We're going to hire 1,111 interns in 2026. So we have a lot of spots to fill. And if your team wins this competition, then you get to skip the line and go straight to an interview. So Cloudflare can do a whole bunch of stuff. And like I say, the competition is just for best use of our developer platform. I suspect a lot of you are going to do AI, so that's what I'm going to focus on today. But no matter what you're building, there's probably something that's of some sort of interest to you. So rather than actually try and do anything for any of the competitions that are there at the moment, I've just thrown together a very quick demo of sort of exploring the data, or at least trying to. So let's see what I've got in my tabs here. One of the very popular libraries that we've published is an MCP library. And for those that are not aware, MCP is the Model Context Protocol. This is a AI basically interface for how LLMs and like your chatbots like ChatGPT and Claude are able to actually take action in the real world. And so sometimes those are read-only operations, things like search, and that's what I'm going to talk about today. And sometimes they are actually going out and like purchasing something or like reserving a ticket or whatever it is that you're doing. So it's a very flexible protocol. And if you wanted to build some project this weekend where users are interacting over natural language, you might build an MCP server so that somebody can just connect ChatGPT up to that, and that can be how they interact with your solution. So if you go to developers.cloudflare.com, there is a page here of documentation on how to get started building an MCP server. You can just copy and paste this command, and let's try and run it live. Let's see what happens. So if I go into folder here, two steps and sizes for you, everyone. Run this. We should have another server. Clones down that template, sets everything up for you, and then you get a new project ready to go that you can start putting in your own like business logic into. So give this just a second. We're not going to use Git, and we're not going to deploy it right now, but now if I go into another MCP server and we open it up in VS Code, let's take a look at what we get. So I'll boost the size again. The source folder has just one file in it. It's a super smart library. It does a lot of the heavy lifting for you. So in fact, in 70 lines here, we have an MCP server. Now, looking at code doesn't tell you a whole lot, but let's actually start this thing. So if I do npm start, there is a cool tool called, let's try and get zoom out of the way, MCP inspector. And if I get this just a second, come over here and check it in here. This is me connecting now to that new project I just set up. If I hit connect, nothing really happens. This is obviously like a debugging view into MCP, but you could equally just be connecting to this, like I say, through ChatGPT or Gemini or Claude or whatever else. You see the two tools that are available here are adding and calculating. So not very imaginative, but this is what I'm saying when you can create tools for these chat agents to be able to use, be it search or purchase a thing or whatever it is that you do. So we can see that 1, 2, sure enough, equals 3. Cool. We used a whole bunch of AI just for that. There exists NASA API for all of the data sets that they have. So like this is them all listed out. And if you grab one of them, you can chuck this in at the top and get more detail about it. And so my plan was to download all of these, pull all of the like title and description from these things, and do interactive search here in this demo. But unfortunately, I didn't have quite enough time. So what have I done instead? Well, if we flip over just to this other tab, it's the exact same project template. All I've done is just change one of these tools. So it's literally those many lines. I've defined a new tool. So rather than just add and calculate, we've now got search NASA data sets. And the first thing we do is a little bit of a fallback. We take the input, which is this string input here, and we're saying, okay, let's just like break that down into the words that are there. But instead, if we can, let's run AI. So I've connected this up to Workers AI. And I'm saying, hey, given the query that the user's provided here, return me a list of words that are going to be related to that. so that I can use it to try and enhance the search that I'm going to perform. So we're saying we're going to do bag of words, possibly related data sets. If the query is find me stuff about weather, you might return weather, climate, temperature, blah, 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 blah. Here's the user's query, return a maximum of 10 words. It must be a JSON array of strings. So quite a few constraints there for an AI, but really good use case where we are taking in an unconstrained input and we're saying, okay, I want a JSON array of all these specific words that are related to the problem. And also you'll notice filtering out all the unrelated stuff. So like if the user's saying please and thank you and all this sort of stuff, AI is really good at just stripping all that out if you ask it to. We then parse that result. And in this case, you could then use any other product to like search through some database. Like you could have a SQLite database or a key value store, something like that, and return some sort of result. And then finally, that goes back to the user. So what does that actually look like when we're running this thing? If we go back to our inspector the other time, here we go. If we clear this, you see we have this one tool. It's in search NASA data sets. We say, please find me data sets about the weather. This thing runs. This is the original query that we got. This is the AI transforming that into related words. So we see that that worked great. And then this is my hard-coded in result of my actual data set that I selected. But like I say, we could take this input from the AI and we could have like done any sort of searching operation over this API that we get from NASA. So yeah, that's pretty much my live demo. If you want to learn more, you can go to agents.cloudflare.com, and we have a bunch of detail here around specifically agents, that's MCP and other AI tooling. So it's a very, very pretty website. I recommend you check it out anyway. And if you're planning on just using Cloudflare at all in your projects, there is the developers.cloudflare.com documentation site. And this has a great overview of all of our developer platform products. There's tons of them. So ones we touched on, agents, we spoke about AI, which is somewhere, workers AI, I'm guessing down here somewhere. Yeah, there. You can use workers itself to host like maybe some interactive like web apps or like D1, R2. And yeah, a bunch of other stuff. So anything that you can sort of dream up, click these things together, and hopefully you have a project at the end of this weekend. So good luck for everyone building, and I'll see you all tomorrow for the judging. Thank you.
You turn on your video.
And the audio, right?
There, see? So it's showing up there once you share your screen. And you
Good.
can start.
All right, but where do I see the people? I see 18 participants.
Since you're sharing your screen, you can't see the people, but they're gonna be like they're here.
Yeah, so is anybody there paying attention? I don't see many people. Oh, a lot of I see a lot of cameras off, so I'm assuming that everyone is there. But thank you for having me. Let me see, somebody wrote something in the chat. Juanita say yes. Oh, thank you. Thank you for inviting me, Andre, to deliver this presentation. I work in pricing, mostly in consumer pricing, and pricing is a very interesting topic, especially when you take into account all the variables that influence price changes. So now, within the pricing area, there is an anomaly that happens very often that is called price gouging. Price gouging is an activity by retailers that typically has bad publicity. It have a bad effect in communities, in people, especially people with from lower socioeconomical areas. And it happens when there are crises, and the crises are typically flooding, earthquakes, fires, hurricanes, all sort of natural disaster. When that happens, some retailers tend to engage in what is called price gouging. Okay, so the idea of this presentation is try to link data, in this case data from NASA, to be able to use with retailer data in order to be able to predict and detect instances where there is price gouging. So here's the definition of price gouging. That's when a retailer is charging in excess for essential goods or services during an emergency. Typically happens during an emergency. And the typical items are water, food, fuel, medical supplies, lodging like hotels, but also transportation, like for example, ground transportation or airlines. When that happens, you will probably notice the prices go like skyrocket, and it's important to look at this because the vulnerable communities are the ones that are being affected. Like typically, when it's a hurricane, people within the affected area are the ones suffering the most, because prices just go out of whack. They increase like really big time, sometimes in a very excessive way, and just affect people. So, however, there is a crisis being created by price gouging, but remember that on top of that, people is also trying to, manage the physical disaster, the hurricane, the earthquake, and so forth. Now, one of the problems for detecting price gouging, it oftentimes is confused with a traditional price increase due to supply chain constraints. Like meaning, some retailers might argue that because there is a disaster zone, it's more expensive for them to bring new products. Therefore, they have to pass a price increase to consumers. So that could be an example, So it's kind of difficult oftentimes to differentiate. The most retailers are, when you reach out due to a price gouging, they will probably say, well, this is what it's costing me. It's just costing me more than I need to pass, the cost to the consumer. So that's traditional case. That's actually, I would say, a legit case of price increases because the the whole supply chain is being affected. But in other cases, it's not just that, it's just greed. It's just what the retailer feel that there is an opportunity to overcharge consumer. So, so price gouging, when that happens, harm communities. So now the detection is hard because what I said before, it's very difficult to monitor. There's a lack of tools for monitoring when it happens. There is, one of the most effective way of, finding is when consumers report it. Like nowadays, consumers are going to a news, to a news station, or they go to social media and they just say and convey that. But that's very imperfect. That's very difficult. Sometimes it's not credible. Social media is not exactly, very credible. I mean, sometimes it's not very credible, and supply and demand shocks, like for example, what happened with COVID. So that happened, and it might look like price gouging, but it's that literally the supply and demand is just making this more difficult for retailers to keep the prices. But unfair pricing, this is a type of unfair pricing, targets these vulnerable groups that are being affected with a disaster. So this idea or this problem is actually an opportunity, creates an opportunity for using different type of data sets. There is an open discussion on how do I measure or monitor for price gouging. One way, for example, could be using NASA open data. There are different data sets that you can use for this. There is a data set that I measure like near real time rainfall and storm intensity. In the US, it's close to real time. Globally, it will have delays. I think it's refreshed every hour or sometimes every few hours. But just give you a very good idea of when there is an excess rainfall or an excess storm intensity that might cause price gouging. Another example, another data set is the firms that measure active wildfire or can be used for measuring active wildfire detections, because wildfire is another case, another type of disaster where price gouging occur. Likewise, in the case of another data set called SMAP that measures soil moisture and flood risk. And in the case of outages, the VERST night lights, I think called Black Marble, allow you to measure for outages and recovery of outages, like outage. Of course, this only happens during the night because that's what data set will be good for. So as you can see, 4 different data sets that can be used alongside retail pricing data to be able to measure, detecting and measuring price gouging. So now here is a detailed description of these data sets. Some of them are giving you a near real-time data. Others, we just need the data to be refreshed every few hours just to get a good estimate. In the case of the precipitation one, we can use that to build a metric called precipitation in millimeters every 24 hours. And then we just build a threshold. And when that threshold is being exceeded, that when we start thinking, oh, there is something happening in this particular community. Likewise, in the case of the wildfire detection via active fire via firms, we can also look for in this case closures in the road to be able to predict supply, what's called supply stress gate, meaning it's going to be very difficult for the trucks. It's going to be very difficult for the supply chains to supply the stores that are in the affected area. Likewise, with the soil moisture L3 or the Black Marble data set that allow us to measure for power loss in the communities. So of course, sounds very cool, just having a data set by itself. But one of the biggest challenges is like, how do I link all this data to the markets? And for that, we rely on a couple of things. Number one, we can overlay the hazard maps using data provided by NASA, with the stores and product data. Meaning we just do overlay, we create baselines, and we measure the different deviation for that baseline. And that will allow us to do some predictions. And the solution can be displayed in many different ways, in a visual way, in a tabular way. You just can create alerts. So there are many opportunities for being able to develop a solution that triggers, an alarm or an alert when something is happening. Now, I'm going to give you an example of 3 different prototypes. I'm going to go a little bit more in detail with one of them, and then I will just give you an idea for the other 2. In the case of the first prototype, which is about detecting an event, we're going to use what's called a detection framework, meaning we're going to estimate the median prices per SKU per store for the last month. Then after that, we're going to measure whether or not there is an event, and that event could be rainfall, fire, or outages. And we see an anomaly. Typically, the anomaly is we have to determine, we have to find these benchmarks. Like, for example, how much of a price increase is an anomaly. In some cases, just a percentage increase from the mean. In other cases, you're going to be just looking for outliers for particular SKUs, particular stores during an event. So we check this based on different contexts, such as inventory, logistic, but also monitoring supply costs. One of the biggest challenges for doing this, because we have the NASA data is open, so we can use it. But what about the retail data? That's very difficult to get. So different ways of approaching this problem. So for this first prototype, which I call it a storm price radar, what you see on the right hand is the actual output for this prototype. And I will give you a link to the GitHub so you can run it and get the prototype running. Every single dot that you see that in that map, every single blue dot is plot is a store being mapped, and then you see the prices and the deviation from prices and flags for every particular store. So this is an example. So for this first prototype, there are a couple of inputs. The first input is the precipitation data and also the flood data, plus store prices feeds. It uses a spatial joint plus anomaly detection, and the output of the prototype is a list of SKUs and zip codes that are flagged, including the stores that are flagged. So an example you will encounter, actually here is a little bit more information about how it works. So you just flag abnormal price jumps only when the stores are exposed to a storm. Of course, this prototype number 1 can be extended to prototype number 2, which just do the same measuring, but when there is fire hazards, and prototype number 3 is when there are outages. And in this particular one, just get the 24 hours rain data. You get the location for the stores in the daily prices for every SKU, every store. And just, the process is, number 1, build a baseline for the last 28 days per store SKU, estimate the mean and the mean absolute deviation. And after that, just compute the deltas, what is the percentage change from the previous baseline. And also just measure the C value for the same absolute difference, because just look for outliers. And what it does is that it just create a flag if the prices exceed the threshold, but also if the precipitation exceeds the threshold. And then after that, you just develop and create a map with the points that are flagged for you to look. So to facilitate this process, I'm making this available. This is a retail data set. It's public. I created this data set for a different purpose. It's a data set of 5 different stores in Manhattan. You have thousands of transactions, thousands of products. And what is very interesting that you have the prices for all the stores, for all the products. You have transactions for consumers. So it's a data set that is open that you can use for validate your model, validate your example. The second one, and you have the link, and Ray, I'm not sure if you're going to get a copy of the presentation.
Yeah, we're recording.
Okay, you will get a copy of the presentation or recording, and so you can see the link. So it's free to use. Free to create a copy of the data set and use that for testing your model. And then the prototype demo is also in a different GitHub, also open for everyone to use. I just created it for this particular challenge, so you can use it. So it has it just read the data from the stores, it read the data from NASA, from the latest for the days in where you have data. I think that the last upload of data for the Mancino database is September, the 25th of September. So as long as you work until the 25th of September, you can run this model and get your outputs very well. There will be another update very soon with more data until October, mid-October, so you can keep practicing and working with this. So I recommend that you just go over the data set and the repository and see how it was done. And the prototype number 2 works very similar to prototype number 1, but in this case, the trigger for an alarm will be the hotspots. Also, it's called the wine plume corridor, which is the smoke that is being created, but also the roads are being blocked, and that's to create, and that's to estimate what is called an stress in the supply chains. I don't think I have much time, right? How long do time?
3 minutes.
3 minutes, perfect. Prototype number 3 works on the, actually, it's a mistake. There is no wildfire supply monitor. It's more a power loss supply monitor. And the idea behind it is that when this sort of disaster happens, there is an extra concern. And the concern is that, there are some particular SKUs that are typically going to increase in price. For example, it's going to be water, ice, it could be diesel. It could be some, products like, water, I was already say water, light bulbs, and, candles, batteries. So these are things that will very likely increase in price during this particular emergency. So we can just focus just by looking on this product. Now, I'm separating these 3 different prototypes just for making them easier to understand. Like, for example, if I go to the first one, to the price reader, I'm trying to make it very easy to understand, but technically speaking, the 3 of them could be just one single product. Just make sure that you can scan for wildfires, you can scan for outages, and also scan for flooding or excessive rain and so forth. So I think I reached out the end of the presentation. I know these presentations are very small, but I'm not sure if we have time for questions. In any case, I'm providing you with my email and also my LinkedIn. Feel free to connect. Feel free to use the repositories in GitHub. The prototype is for you. I made it for you. And the data set, I made that for my classes, but you are also very more than welcome to use it. Okay. So if you don't have questions, thank you so much, and look forward to see you soon. Oh, I have a question right here. Can you repeat when we found? Yes, exactly right. The repositories. Right here, Juanita, can you see it in the screen? https://github.com/
Right now, I'm not being able to see the screen.
Oh, I'm so sorry.
No worries.
Then it's a problem. You can see the screen. Let me put it right here. Sorry. Hey, how are you?
Recording in progress.
Let me put it right here. GitHub.com/, yeah. That's So the one I put in chat is a prototype for the price reader. And the second one is going to be the prototype. It's not a prototype, it's the data set that I use for my classes, but it has contained retail data that you can use for your exercises and for your project.
Thank you so much, Jose.
Thank you so much. Okay. All right. Thank you. Bye-bye.
Thank you for the presentation. Take care.
leave the meeting. You can leave.
All right. Hi, everyone. My name is Kenechukwu Ezekwem. You can call me Ken. Quick show. If you've used ChatGPT today or at all, then you are very familiar with what I want to talk about today, even though you may not be aware that you're very familiar with it. And what I'm about to talk about today is called embeddings and how embeddings can help us improve data for machine learning. So when you talk to ChatGPT, you give it words, right? The words it turns to tokens. So something like spacecraft will become space and craft. Now those tokens get turned into embeddings, which is typically a high dimensional vector space, typically about 3,000 vectors for most embedding models, which capture meaning, semantic meaning. Then that semantic meaning is then passed to the transformer architecture of a machine learning model, which now helps it predict the next token, convert it back to embeddings and back to text for you. And if the embedding model is a multimodal model, you could pass more than just text. You could pass images, you could pass audio into that. So today I'll be talking about feature engineering, reimagined, using embeddings in general. So we'll first start with discussing what embeddings are, and I'll keep it as simple as I can. And it's like coordinates on a map. You know, if you've used Google Maps, you would understand it easily. Then I'll walk you through an experiment that I ran with this and the results we got from the experiment, okay? Then from there, we'll talk about the results and why we have the results we have. We'll compare that to other results others have had. And finally, I will create or discuss a 5-step process for anyone that wants to do something like this. And hopefully I can do all this in 15 minutes or less. All right. So we'll talk about embeddings. So when you send, like I said, words, or you send an image into your chat models, or even audio when you talk to it, or video for some models that are powerful enough to understand video, they first encode it, they first tokenize the image coming in, then they encode it into embeddings. And those embeddings are nothing but an array of numbers, right? And these numbers capture semantic meaning. So something like king and man will be closer in meaning, and they will be closer in the vector space. Something like queen, woman, Paris, France, New York, Eiffel Tower closer together in the space, in the model, in the embedding space. And we'll discuss what this means for feature engineering. But the conventional way, which I'm beginning to call the old way of doing feature engineering, is some sort of manual feature engineering or manipulation of the data. Sometimes, let's say you have a feature or a column that is the population of a city, and you have another one that is like the square area of a city. You could do a ratio of that to get population density, which helps the model understand what you're trying to study more, depending on the context of what you're trying to study. Now, that is good, and we've used that for a very long time, but they have limitations. First, it requires domain expertise. It is brittle, and it's difficult to port from one context to another. So using a ratio of 1 over the other may not transfer if I move that to healthcare data or if I move that to any other type of data, right? So what's the alternative? Well, for the past 5 years, there's a growing trend now in feature engineering, which is, we're going by the term now representation learning. So you pass in certain things into the embedding model, and they return the vectors that they normally would send into your ChatGPT model transformer architecture. And from those vector embeddings, you will find more meaning and semantic information that is stored in there, right? And there are multiple ways you can do this. You can do row-wise, send in every row in your data in there, and you can capture meanings of everything you're talking about. So if you look at the slide currently right now, you will see we're trying to visualize something impossible, right? So it's not easy to visualize anything more than 3-dimension, right? But if you look at this, you'll find that something like a coolant is missing, and if it is leaking, or there's a pressure leak or issues like that on a spacecraft. If you put that in an embedding, they'll be closer together. Those are issues. It has to do with spacecraft and all that. But if there's nominal operation, it's going to be far away in the embedding space from the issues, right? So we'll see what this means for us. So when you think of vector embeddings, think meaning captures in a semantic way, represented in numbers, which is the only way computers understand stuff, right? For now. So one way we can compare how two ideas, words, sentences, phrases, or anything you turn into an embedding, how they are close together is using cosine similarity, measuring the angles between the reduced dimensionality of the embeddings, all right? So to demonstrate the potency of this idea, I designed an experiment using 1,500 rows of spacecraft maintenance records. Synthetic record, of course, but designed for this experiment. Now, the features of these records are temperature, pressure, vibration, the subsystem that could have the issue, and engineering notes that the engineers may just write, which is freeform and not exactly tabular data. Now, the test is to have two versions of the data set. One that has these features that we've listed on number 2 on the slide, and another that has these features, but with 128 embeddings captured for each row returned to it, right? Then we'll pass both into 4 regression models, one simple model, logistic regression, and other tree-based models like the random forest, the GB boost, the XG boost, and we'll use 5-fold cross-validation to ensure that our calculations and modeling is done correctly. So what does that mean for us? Now, this is a sample of what this data set looks like, right? So here we have a note of temperature, pressure, vibration, and communication, the subsystem we're talking about, and simple notes that normally would be hard to work with. That's put down by the engineer. Then we have 1 for if that subsystem requires maintenance, and 0 when it doesn't require maintenance. So the real question is this: what happens when we add 128 additional columns, which is the embedding generated from just the notes column of this data set? So we'll find out what that means for us, okay? So we ran an analysis using both the traditional conventional method and the method with embeddings. And what did we find here? we found an average of 10% boost in accuracy and an increase in area under curve and ROC numbers. Now, the surprising thing about the results we got is that logistic regression saw an improvement that was even more than the gradient boosting model. Now, this tells us that with just embeddings, you can improve your data set to capture enough meaning that simple interpretable models can still be used to achieve high accuracy, where you can still work with the interpretation of the model to some extent, you know? So here is a breakdown of all the results we got for each of the models. So we have the baseline accuracy, running it without embeddings, which, I mean, it wasn't too bad. Then with the embeddings, you can notice a boost and a jump in, accuracy of the models, with XGBoost gaining the most and them having an average of 10%. Now, how does this result compare to other studies that have been done for the past 5 years in this? Quite similar. Literature review shows that adding embeddings have increased accuracy from somewhere between 3% for tabular data used in classification to about 17% range. And this is when you use small embedding models that are kind of more affordable or free to use, like the one I used for this study. They're bigger embedding models that capture even better meaning that haven't been used in any of these studies, right? So why did this work? Well, one of the ways we'll try to look into why this works is reducing the dimensionality. Like I said earlier, there's no way to visualize 127 dimensions in space. So I'll use principal component analysis to break down the 128 dimensions we got from embeddings into two-dimensional spaces so that we can see what we got back from the model that helped prediction. So, which is the plot we have here. Now, if you can see from the plot here, everything you have in purple, the NYU purple here, shows we need maintenance. And everything we have in the other colors shows we don't need maintenance there. And the reduced dimension from the meaning we got from the embeddings, it somehow captured that certain things need maintenance and certain things don't need maintenance. So if you draw a straight line that is vertical from 0.2 all the way up, you would observe that all the maintenance, all the places that need maintenance lie in one place on the two-dimensional space. And such semantic meanings, we can always get that when we send each row of our data into an embedded model to capture back the vector arrays, which normally will be sent into the GPT model or its architecture to predict the next word or the next audio or the next video or anything. But in this case, we're just capturing the vector embeddings. So if you want to replicate something like this, the first thing you would do is to pick an embedding model. The second thing you do is to generate the embeddings for your data set. I would recommend saving it once you generate it once so that you're not running your API calls each time you run a model. Then the third is you do your search. You search for anomalies. You search for drift in data. And the last is to do an A/B testing, a controlled experiment of one with and one without this information to find out what the difference is. And sometimes we found that when you fine-tune your embedding model to be more specific to your area, to your specialty or your area of interest, the performance increases drastically. So for NASA, rather than using the general embedding model that I used, we could fine-tune the data to be more of a NASA kind of data. And studies have shown that that gives you a boost in accuracy of +5 to +15% range. So I'll leave you with this. I want you to think about the more than 200,000 publications and research that have been, peer-reviewed and put out there, which have to do with classification and tabular data, and revisiting most of them with the power of embeddings now to improve the accuracy. What does that mean for science? If all the accuracy we can get above everything we've done before just increases marginally by about 10%. Now, that's the question I want to leave you with. And with that, I'll say thank you, everyone. And if you have any questions, please let me know. Thanks.
It's a pretty epic question.
Thank you.
Awesome. Start your minutes, I guess.
You're ready to go? Ready to go?
Great. You, you accepted me in the Zoom from your call right there. Yeah, and let me access it.
No, that's a co-host.
Oh.
I can push it.
Yeah.
Yeah.
It was traditional, like, I think I can move straight.
We'll just wait until 2:30.
Yeah, yeah. Cruising around the sun.
Hey, it's Micah. Alex, you're good to go. I can
Um,
hear you.
Hello, everyone. My name is Alex Burg. I am employed by the Aerospace Corporation. I work at NASA headquarters in the Strategy and Architecture Office of the Exploration Systems Development Mission Directorate, which is the part of NASA that focuses on human space exploration beyond low Earth orbit, so going to the moon, Mars, and so on. I'm here today to talk to all of you, to give you a little bit of an overview of what a lot of the future of human spaceflight looks like over the coming years. This has been a very software-focused weekend. I'm here to talk a little bit about the hardware that we've got going on. So Artemis is our our mission to return humans to the moon. The name of it in Greek mythology, Apollo's younger sister, is named Artemis. And so the idea is that Artemis is picking up where Apollo left off. We've got a lot of different pieces of this that are coming online. We've got the Space Launch System, the SLS, that's our new big rocket, sort of the successor to the Saturn V. We've got the Orion spacecraft, that's where the humans will be living, the Human Landing System, which is actually going to land on the surface of the moon. Those are being developed by both SpaceX and Blue Origin. The surface operations, we've got the Gateway, which is going to be orbiting the moon. We've got ground systems, communications, mobility, spacesuits, surface infrastructure. There's a lot to cover. Try to go over everything in a briefly, and then also talk about how all of this leads to us going to Mars in the future. So we have here, NASA has signed an agreement with many countries throughout the world called the Artemis Accords. This is essentially, we're all on the same team, more or less, in terms of working together for common purpose. In many cases, NASA is sort of like setting the table, and a lot of different countries that NASA has signed agreements with are essentially filling in the pieces kind of all over the place. So yeah, I think there's 56 countries and counting, expecting more over the coming years. But it really is truly a unified global team effort to go back to the moon. Very exciting times. Next year is we're going to be orbiting the moon for the first time with astronauts since Apollo. Just to give you an idea of how NASA itself thinks about all of this and the flow of infrastructure over time, is that there's the initial human lunar return, right? That's going to be very much like an Apollo style mission where we go back to the moon, plant our flag, announce to the world we're back. But that's where the similarities with Apollo end, is at the very beginning. After that, we're going to be leading towards the next stage, which is called foundational exploration, which is really working towards expanding these lunar capabilities, working towards long-term infrastructure on the surface of the moon, additionally building more orbiting infrastructure around the moon, doing surface missions, doing a lot of interesting science utilization, as well as preparing for going to Mars. The moon is one of the best places to test and prove a lot of the technologies that we need so we can actually make it to Mars. Sticking on the moon path, that will all lead to sustained lunar evolution, which means that the end goal of this is to actually have humans on the moon at all times, 24/7, 365 human presence on the moon. But as I was saying, we're going to be eventually sending humans to Mars. We're focused, sort of the horizon goal right now is that first human mission to Mars. We're working on the initial capabilities to establish this, to eventually land humans on Mars and then return them back safely. And as we continue expansion on Mars, that will continue out, then leading to future segments. Those are TBD right now, but that's going to be Mars and beyond. So let's bring it back in. So why the moon? It leads to new discoveries and returns that are of incredible value to all of us here on Earth. It advances civilization. From the US perspective, it establishes American leadership and strategic presence. We can prove out technologies for Mars, creates opportunities and economic growth. And it also inspires the new generation to build careers in STEM. All of us are here because we've been inspired by space to some extent. So we want to do that once again for the next generation. So let's talk about some of the actual technologies that we're building for this purpose. So here's a sense of scale. You see here the SLS and Orion Block 1 and 2. These are these heights taller than the Statue of Liberty. Saturn V, a little bit taller than the Block 1, but the Block 2 is actually 1 foot taller than the Saturn V. The Block 2 is essentially the next stage of it, with a little bit more advanced. but yeah, I mean, it's very big, it's very tall. SpaceX's Starship, it's not pictured here, but there it is also of comparable scale. So we're talking really big rockets, very impressive stuff. The first one of these successfully launched back in 2022, and the next one is going next year. But at the very top of these is going to be the Orion crew capsule. And this is going to be roughly what it looks like when it's in space. The astronauts will be living there inside of it for the duration of their voyages. When it's broken out, here's basically what it looks like. You've got the crew module on the inside, you've got your abort system, your jettison motor. It's pretty standard stuff. The European Space Agency is also contributing to this in the service module. Yeah, pretty standard stuff that as compared with what's happened before, but obviously much more updated and newer technologies and so on. So Artemis 1, it already happened in November of 2022. It was uncrewed. The SLS rocket, as long with the Orion crew capsule, purely autonomously went, orbited the moon, and came back. Everything's successful. Now that we've proven it out without people, the next step is to include people in the mission, and that's where Artemis 2 is happening next year, sometime spring of 2026, so quite soon. 4 astronauts will be orbiting the moon and then returning without landing, and then Artemis 3, which is tentatively scheduled for summer of 2027, is going to be astronauts actually returning to the surface of the moon for the first time since Apollo. So to give you all a sense of what Artemis 1 actually looked like, this is what it is. This is the path that it took. These were the trajectories. And pretty interesting stuff. Pretty exciting, but this is just the beginning. Artemis 2, on the other hand, in some sense, it's a little bit more straightforward, but since there's humans involved, it actually ends up being a little bit more challenging, but it's really all essentially incremental progress to prove out that we can actually send humans to the moon. And then Artemis, and but it's really being built. To give you all some updated pictures, it's all happening. These are pictures as of this year. The hardware is close to completion, where just a matter of months until it actually launches. Yeah, it's really exciting stuff that it's actually being built to send humans back to the moon. Let's go to the next slide. And then Artemis 3, which is going to be similar but different. You're going to send humans to the moon. There's going to be an insertion into a near rectilinear halo orbit, which we'll get into in later slides. And then from there, the crew will be transferring to the human landing system from the gateway, most likely, and then going to the surface of the moon at the South Pole. So that's another interesting difference between Apollo and Artemis, is that during Apollo missions, we had 6 landings on the surface of the moon, and each of those were at different points close to the equator. This time we're going to the South Pole. Why are we going to the South Pole? Well, we have long exposure to sunlight, which creates environments that are suitable to long duration survivability of hardware and infrastructure. There's also some really interesting opportunities for sample collection that can help to identify the actual age of the largest impact basin in the solar system, which can help ascertain when life might have been able to survive on Earth. So we can begin to start answering some questions about the beginnings of life here on Earth by dating the South Pole of the moon and the crater impacts there. Additionally, there are lots of volatiles, which are essentially trapped as ice in the South Pole's permanently shadowed regions, which can reveal inner history, or this history of the inner solar system. And also there's potentially quite a bit of water that's there at both poles, but especially the South Pole, there's more. And if there's water at the South Pole of the moon and it's frozen, but if we can harvest it, then, well, we can think about setting up a civilization there, frankly. We could drink that water if we can process it properly. We can use it for industrial processes. It could be an ingredient in rocket fuel. There's a lot of different possible applications. Right at the South Pole, one of the most interesting craters is called Shackleton Crater, which you may or may not have heard of. To give you a sense of scale, Shackleton Crater is roughly the size of Washington, D.C. It's a little bit deeper than Washington, D.C., but it is just it's definitely a very interesting place where we believe we can go down there. There's potentially some really interesting opportunities to get some water that we can go drive around and harvest it. So yeah, it's definitely a very interesting place. It also is, yeah, it's deeper than the Grand Canyon. It's roughly twice as deep as the Grand Canyon. So building technology that can go drive on that without any roads into these really cold places without any sunlight, that is a challenge, but it also presents a very exciting opportunity. But yeah, Artemis 3, it's coming along. We're at this point, hopefully less than 2 years away. We've been making quite a bit of progress. A lot of the hardware is actually being built. We've got the Axiom spacesuits that have been announced. We've got a lot of the core stages being built. Everything is coming together for this less than 2 years in the future. But that's going to take us to orbiting the moon, but it's going to be an actual Starship human landing system that's going to land on the surface of the moon where astronauts are going to get out of. That's also being built. There's a lot of media about this. Starship is coming along very nicely. And so SpaceX has won the award for Artemis 3 to land humans on the moon, and that is also being built. There's a lot of progress being made. What's also interesting about this human landing system is that humans are going to essentially be living at this first mission at the top, and there's going to take an elevator down to the surface, and then once they take the elevator down to the surface, then they're going to go walk around and do all the things that we're excited for the astronauts to do on the surface of the moon. And so it's just a really interesting, exciting opportunity. But I also mentioned before that there's going to be some infrastructure that's going to be orbiting the moon. The main component of that is called the Gateway. The Gateway, it's called that because it's exactly what it sounds like. It's going to enable us to send more infrastructure to the surface of the moon if we build this. It's not quite a space station. It's a spacecraft because humans will be living in it sometimes and it will be autonomous other times. And to give you a sense of scale, imagine 2 school buses stacked one on top of the other, and that's the size that we're talking about here of the Gateway. So it's going to be substantially smaller than the International Space Station, but still can do all kinds of very interesting things. It's going to be in this very unusual orbit, which we'll briefly cover. It's going to be a polar orbit around the moon, but a special type of polar orbit, called a near rectilinear halo orbit. And essentially what that does is that it's going to allow us to maintain almost entirely communication between the Gateway itself and the south pole of the moon where the astronauts will be, as well as having almost always a line of sight with the Earth. And so it's really going to allow for a constant communication. Definitely very exciting. But it's going to be in this near rectilinear halo orbit. It's not actually going to be orbiting the moon. It's going to be orbiting a Lagrange point around the moon. The Earth-Moon Lagrange point 2, which is beyond the far side of the moon. You can orbit Lagrange points, and so it's going to be orbiting that Lagrange point. And because it's orbiting the Lagrange point, so technically you're going to the Lagrange point, and then from the Lagrange point orbit to the moon, that allows you to increase your throughput of mass you can send to the surface of the moon if you engineer different systems to be customized for each of the different pieces that they're for. So one technology is customized for going from Earth to the Gateway. That's going to be SLS and Orion. And then you also have the human landing system, which is a taxi service essentially between the Gateway and the surface of the moon. And so when you build this customization, you can increase how much you can send. It also allows you to send more technologies from the Earth-Moon system outside of our combined Earth-Moon gravity well to Mars, for example, which we will cover. So the Gateway, it's going to be this initial capability, simple, just the power and propulsion element, just your basics to survive. Eventually, there's going to be also the habitation and logistics outpost, the Halo. 4 people can live for up to 30 days within it with Orion. You can do all kinds of interesting science with people and different types of science without people. So it allows you to have that bimodal functionality. And it also allows us a docking port. So like I was saying, the Orion crew capsule will dock with the Gateway. At the same time, there will also be the human landing system. And so the astronauts will transfer from the Orion through the Gateway into the human landing system. And then from the human landing system, go down to the surface of the moon. And also when they're coming back up, it will be the reverse process. And so that it's just an interesting new model that we're using for this. You know, there's going to be some interesting science that's going to be there. European radiation sensors, also the ESA internal dosimeter array with JAXA, the Japanese Space Agency. NASA is also building the heliophysics environmental radiation measurement experiment suite. Really is a lot of just really interesting capabilities, but we're also going to be building it out over time. There's going to be another Canada arm, which is really cool. That's going to happen. There's going to be a secondary habitat that's going to be built by the Europeans. So there will be one, then eventually two habitats, habitable modules, I should say. Japanese Space Agency is also building more interesting environmental control systems, and the UAE Space Agency is also building an airlock module. So it really is an international effort. Different countries and different groups around from all over the world are building something together, orbiting the moon. But we're actually still building it. There's a lot of this hardware. The metal is already being cut for this. It's going to go up soon. Things are getting very close to fruition. So let me also now I've talked about a lot of the big hardware. Let me talk about some individual systems. We have this advanced spacesuit, which is coming online that NASA selected Axiom to develop this totally new modern type of spacesuit for Artemis. As compared with a lot of the bigger ones, it's not quite as bulky as the ones you've seen in the past. It's going to increase flexibility for exploring new regions, more advanced sample collection, increase size, range, design, so you can do more things. There's rechargeable systems, so you can have more spacewalks and stay on the surface longer than during the Apollo era. A lot of specialized tools that we can use when we're going and sampling the moon. It's really just the next generation in the progression of all of this. Just to give you another high-level overview, there's a lot of architecture elements that we're building on the moon. This is not even all of them, but there's a lot. There's a lot that we're going to be building very soon. And I'm excited to talk about some of them that have already been announced. For example, it was announced recently that we're going to be building a fission power source on the south pole of the moon by 2030, I believe 100 kilowatts, which for reference is enough to power a small to medium-sized building here on Earth. We're going to have that power source on the moon, and it's going to provide us reliable power that is not weather dependent, doesn't matter the sunlight conditions and so on. And it's going to power our lander systems, habitats, allow for in situ resource utilization, provide its power through eclipse periods. It's also a proving ground because we want to build something similar for Mars. And so this allows us to do it earlier. When we're on the surface of the moon, we're going to be doing in situ resource utilization, or ISRU for short. It's going to allow us to essentially do mapping of resources that are on the moon, extract oxygen and water, and potentially other metals beyond that as we further properly characterize the surface of the moon and eventually for Mars, doing something similar. And it also is going to allow us to actually perform construction on the moon. So if we can harvest these resources from the moon, like I was saying, we could map the water, extract the water for drinking and industrial purposes, something similar with oxygen, but also metals and rocks and so on. You could think one day that if we can extract these and then put them into an industrial processes, we can build roads on the moon, launching and landing pads, which are very important because instead of all this dust every time we take off and land, we can actually build a real landing pad. Then you don't need to worry about all of these ejecta going everywhere, and you can just have your landing pad, which can be reusable. And that means that you can actually build your civilization closer to where you land because you don't need to worry about the dust getting kicked up everywhere. So that's actually can be a very high priority once we have this technology built. It also allows us to build radiation shields, various shaded structures, unpressurized shelters, and even eventually one day pressurized habitats. So it's really interesting opportunities for developing the moon. There's also a private sector aspect of this. So NASA has something called the Commercial Lunar Payload Services, where if you've seen a lot of these things, where there's these missions that are landing on the moon in the past few months, that is all through NASA's Commercial Lunar Payload Services program. It's been very successful so far, and it's growing. And it essentially, right, so there's been 4 providers and counting that are currently on contract for delivering payload to the moon. There's a lot of different exciting new technologies and science opportunities that are going to be done on the moon through this. And basically, NASA solicits bids from various companies and awards contracts to actually deliver science, exploration, and technology payloads to the surface of the moon. It's only growing. It's only growing. It's only getting bigger. It's very exciting. But that's as time goes on, we're going to be building all this out on the moon. But let's switch gears to Mars a little bit. So around the gateway, we're going to be building our vehicle that's going to take us to Mars. And the main piece of this is going to be called the transit habitat. It's going to be reusable, designed for 15 years of life. It's going to keep the crew healthy and productive during the long duration from the Earth-Moon system all the way to Mars and back. It's going to be tested out around the gateway, all kinds of proving ground experiments and so on. It's going to be able to survive for the roughly up to 1,100-day Mars transit and orbital stay. So we're talking on the order of 3 years potentially for the round trip. So, you know, it demonstrates its needed capability to live for long durations beyond low Earth orbit. And it also builds on what we've already done in the International Space Station and commercial investments in deep space habitation. But how does the moon actually allow us to go to Mars? There's a lot of similarities. Some stuff is the same and some stuff is different. A lot that's the same, we can experiment with long duration in zero or microgravity. We can experiment with varying crew sizes and what that means. Mobile expedition, so we're driving on our rovers on the moon. There's still a lot that we can learn about Mars through doing this. Fission power, like I was mentioning, resource utilization. So while Mars and the moon obviously have very different chemistries, they're different worlds, the act of trying to perform in situ resource utilization on the moon does have some analogous capabilities and functionalities for Mars. It also allows us to operate in partial gravity and learn what that's like. And there's various autonomous and robotic operations also that we're doing on the moon. We'll be doing potentially some similar things on Mars. Furthermore, so, you know, Moon and Mars architecture, there is a lot in common, like I was saying. Deep space aggregation, habitation, orbit to surface operations, refueling, crew health and performance. Just what does it take to live in space for a long period of time? We can learn a lot on the moon before going to Mars. Spacesuit advancements, mobile ops, planetary protection, so making sure that we have a lot of contamination that can go both ways. That's kept to a minimum. Robotic and human exploration and resilience. You know, a round trip mission to Mars is going to take somewhere between 2 to 3 years. As much as possible, we want to design our moon systems to prepare us for going to Mars. And so these integrated missions in lunar vicinity can really help prepare us for Mars, and really it's essential. But then the question is, well, why Mars? Well, it's our nearest habitable planetary neighbor. It's got a lot of natural resources, oxygen, we can extract from ice or even atmospheric, CO2, water, iron, sunlight. And the rovers that are there only explored a fraction of Mars's surface. There's immense opportunities along with immense challenges. To give you a sense of what Mars is like, the solar day is called a sol. It's a little bit longer than a day here on Earth, 24 hours, 39 minutes, and a little bit. The Mars mission, it's going to have a round trip communication delay of up to 44 minutes for a signal and back. So we really are going to be autonomous in many ways. You know, if you're orbiting the space station or even on the moon is a 1 second delay to Earth. So 1 second versus 44 minutes are completely different paradigms. You really are on your own. So you need to design things in that mindset. The weather on Mars also is very different. The atmosphere is 1/100th of the atmosphere here on Earth. And also made up of different things. As you can see, Mars is almost, while it is 1/100th of the atmosphere of Earth, it's also almost entirely carbon dioxide. There's almost no oxygen to speak of. But it does have an active weather system. We see annual dust storms and global storms are less frequent, but we also still haven't even fully characterized the weather on Mars. So there are uncertainties and unknowns about this even before we go. So we're actively trying to learn as much as possible. The landscape is also quite different. You know, as you can see on the right here, there's this one giant canyon, which is roughly the entire length of the United States. So it's really huge. It's much bigger than the Grand Canyon for a sense of scale, bigger and deeper. There's also giant mountains. So Olympus Mons is the largest mountain in the solar system. Just to give you a sense of scale, much bigger than Everest. It used to be an active volcano in the past, no longer. The entire size of it is roughly the size of Arizona, for a sense of scale, from the bottom to the top. So really enormous. Talking about some transportation challenges, going to Mars is going to be unlike anything that anyone has ever done. But it's the same amount of energy to get to the moon and back always, because the distance is the same, but it varies when we're going to Mars and back. A lot of that is a function of Mars gets progressively closer and further away because it has its own orbit around the sun. But the energy that we need, like I said, it varies. Sometimes it requires 20 to 60% more energy in one year versus other years based on the distances and the orbits. And the transit propellant mass variations have the potential from one transit versus another based on the proximities of Earth and Mars to be equivalent to the entire mass of the International Space Station. That's just the delta in fuel mass. So we're really talking about a scale bigger than anything that we've done before. And it's like when a mission departs, it affects when it can go back and how. And these capabilities, everything is so interconnected for transportation, aggregation, reliability, the opportunities. It's constantly, everything is so interconnected. Every 26 months, we have a launch window. But we're going to take off from the gateway. Like I was saying, around the gateway, we're going to build the Mars transportation vehicle and then go to Mars and back from there. And so it's just a new paradigm. It's just like I said, it's unlike anything else. Some interesting aspects of this is that we actually don't know which type of transportation system we're going to use. We might be using chemical stage from your more traditional chemical propulsion. There could be some hybrid variations between chemical and nuclear electric propulsion or nuclear thermal propulsion, solar electric and chemical, all chemical. It's all still open for debate and discussion and analysis. There's also cargo variations for what this might look like. There's all these different options. It's all being worked actively right now. Even just to give you a sense of scale for landing humans on Mars, this is what we've landed on Mars so far, the size and the mass. So we're talking 1 to 2 orders of magnitude bigger for anything that we're landing on Mars for human scale compared with anything that's happened in the past. So it really is a totally new paradigm. We're going to be using some type of supersonic retropropulsion, and it's just totally new technologies as compared with anything that's happened before. Additionally, we don't know how many people we're going to send. There's a lot of crew complement considerations. We need to send enough crew to complete the mission goals and maintain vehicle functions and respond to emergencies and contingency events. But at the same time, the more people you send, the more of a stressor it is on your resources and your life support systems and your fuel and everything else. And so there's a real balancing act. And so then there's the question of how many to send to Mars, and then of those that you send to Mars, how many actually also go to the surface? Maybe some stay in orbit, some go to the surface. And if some that go to the surface, maybe some do EVAs, or maybe everyone does an EVA. No one knows the answer to this yet. Everyone's figuring this out right now. And also, what's the right skill mix that's needed? You think about, like in Star Trek, you have your away mission. These different people with different skills. What does that skill set look like? And what roles people need to train for? All of these things are actively under consideration. And like, what are some of the crew time considerations? How do people sleep? Personal time, science, exploration, public engagement. All these things, what's this breakdown? This is all open for debate. There's also, what does the Mars spacesuit look like? You have to account for radiation, isolation, distance from Earth, reduced gravity, hostile environments. There's a lot of uncertainties that's associated with this. And even living and working on the surface, you have terrain hazards, planetary protection concerns, communication latency, dust storms. These are all questions that people are actively thinking about. And no one knows the answers to a lot of these things, quite frankly. If any of you are interested in working with NASA, feel free to scan this QR code that you see up here. There's a lot of opportunities for working with NASA in the future. Everything is only getting closer and closer to achieving all of our goals. And with that, here's my contact information if anyone would like to reach out to me. And thank you very much. go back up to this one if anyone wants to take some more time to scan this QR code. Yeah, okay, thanks.
I just muted the mic. You muted the mic.
Oh, no.